All right. Good morning, folks. Hope you guys had a good Wednesday. I didn't see anyone yesterday, so if you do have questions, then please, I want to keep reminding you. Make sure you come by and you see me and get your questions answered. Um, I hope then that meant that the Fit Lab ran pretty smoothly. I hope you had the chance to explore that Fit Lab a little bit more. It is a very useful Fit Lab, you guys, to help you understand projectile motion. I've been using it for quite a while. I really am a big fan of University of Colorado for making these FET labs for us. But I particularly like this one because in the past, studying projectile motion and actually running the lab using a physically going out in the field and doing it made it a bit difficult because remember, out in the real world here, we cannot ignore air friction. We can't ignore air friction. And so, and we're studying projectile motion by assuming first and foremost, one of the more important assumptions that we're making is that there is no air friction. Okay, so the Fit Lab here allows you to explore that. You could have done this. You could have done the Fit Lab just using either the introductory activity, or you could have used the lab as well. But I hope that you explored one of the other two, the vector ones as well. And I'm going to actually start out today with that to kind of just recap for you what we've talked about up until this point. And then from there, I want to work out that sample problem, finish working out that sample problem for you so that you can go ahead and finish up the homework. If you look on Classroom, I have modified the due date for the homework. And I'm sorry, let me go ahead. I forgot this. I should probably start this before I keep going. Keep me on track, my watch. All right, but I've modified the homework. It is not due until tonight. And so please stick around after, hopefully a few of you will stick around after I take roll before you start watching the video here. But if you're watching the video now and you do have questions, just pause the video and come back and get your questions answered. Okay, but I will finish going over that problem for you with the long jumper. And then I want to work out a few more problems with you, involving projectile motion so that you will have some comfort level with it before we continue on with the rest of this chapter. And so I would like to go on and I want to try to finish up with the projectile motion on Monday. I apologize. I forgot that we don't have class tomorrow. And so and the lesson on Monday, I would like to, and the hope is to get started with rotational motion then as well. Okay. So let me go ahead then, and let me share with you my screen here. Let's go ahead and let me go and do this here. All right. So this is the lab that you're familiar with right here. So like I said, many of you probably used the introduction here, the introduction activity here in order to get acquainted with the lab here. Okay. Or you could have used the lab, the actual lab here itself as well. They both kind of offer the same opportunities. They offer the same type of manipulative controls. Okay. What I'm going to do is I'm going to use the vector quantity, the vector option here. So I'm going to go ahead and click that on. Okay, and let me open this up for a full screen here. All right, and so hopefully you were able, and again, if you notice here, the tools are pretty much the same as well. The only difference is in this particular one, the only option we have here is the cannonball. Okay, but in order to measure out the range, okay, so hopefully remember the range is the horizontal distance here. You could have used this tape measure here in order to measure out the range. You got to make sure that you set that tape measure out pretty close to the cannon, and then you can measure the range of where the object lands. Okay, so the range then is the horizontal distance. You can also use this to measure the height as well. Okay, you can measure the vertical distance as well by just turning it around. So that's one option that you have for measuring the range or measuring the vertical distance, the height. Okay, so range versus height. Now, the other option here is this little gauge, gauge meter here, I suppose. Okay. What you could do then is you could place the little bullseye here, right? I'm sorry, the little target aiming piece here, right on one of the locations of the moving object along the projectile motion. And it'll give you the time that it took to get to that position, the range, and also the height. Okay? And so a couple tools here that you could have used. Hopefully you had a chance to use them as well. But furthermore, hopefully you were able to play around with this bullseye here, and you can move it around and get the distance as well, the range as well. Okay. All right. So what did I want to do? What do I want to do with this particular FET lab here? Well, I want to go ahead and I want to show you something here, and that is I want to share with you the different ways that we can represent the motion. Okay, so with the vectors here. So if you notice here, then we can click on the options here for the components of the vector, the velocity vector, acceleration vector, and the force vector. Now, in order to get this done, remember, when we're studying projectile motion, we're going to ignore air resistance. Okay? So what I would like to do then is, first and foremost, I want to show you, we said then that when we shut off that air resistance, there's only going to be one force acting on an object, this cannonball here, as it gets shot out of the cannon. It's going to assume this projectile motion, that parabolic motion that you're going to see. Okay? It's going to assume that. And what you're going to notice then is that if there is no air resistance, that there should be only one force acting on it. So I'm going to click that on, and then I'm going to click this in normal here, and I'm going to fire off the cannon. I'm going to pause it at certain points here. So as you notice, as the cannonball leaves the cannon, there's your force vector right there. And if you notice, then there's the weight. So the only force acting on the cannonball as it leaves and it starts to fly up in the upward trajectory, the only force acting on it is the downward pull of gravity. And as I unclick and as I unpause this here, you're going to notice that at every point along the way, every point along the pathway here, if you take a look at this, the direction and the only force acting, even at the very top here, the only force acting on the cannonball is the gravitational force, and in the downward direction. The gravitational force is always going to be in the downward direction, and it will always stay the same. And if you notice then, because there are no other forces acting on that cannonball, then the net force acting on the cannonball is simply going to be the force of gravity. There is no normal force. Again, there's no normal force because the cannonball is not making contact with any surface, okay? And there's no air friction. Okay? And so the only force acting on it is going to be gravity. Okay? Which means then, if I let me go ahead and annotate, share with you a few things here. Okay? Which means then, if we take a look at this, okay, that if we were to write out the Newton's law here, so Newton's law, then remember then is going to be the sum of all the forces. And so therefore, the only force acting on this object right now is going to be the force of gravity. Okay, so that's what you got to make sure you understand. So therefore, then, if we write this out, remember the sum of the forces then is also going to be equal to mass times acceleration. That's Newton's second law. Combining these two, then you're going to notice then that the only force acting on it, if it's going to be gravity, is the only force acting is gravity. Therefore, the only acceleration acting on this object is going to be gravitational acceleration, which is what I'm going to point out to you next. Okay? Now, with that said, the last thing I want to point out to you is this: all along the pathway here, hopefully you're going to notice then that the force of gravity also does not change. Okay? So as it moves, the length of that force vector here stays the same, even when it touches the ground, and then the motion is complete. So the idea that I want to get across to you here, and what I've been trying to get across to you, is that if we ignore air resistance, the only force that we have acting on is gravity. So therefore, and gravity is always downward. So let's take a look at the acceleration vector. So if that is true, okay, let me go ahead and clear that up. If we take a look at this, we expect then that all along that same pathway, the only acceleration, whoops, no, I'm sorry, let me try that again. That up. Okay, so as it leaves the cannonball right there, there's your acceleration vector. And if you notice then, it is also downward. And so now we know that this acceleration vector right here is the gravity, it's gravitational acceleration. So therefore, it's going to have a value, we know that of 9.8 meters per second squared, and it should be downward. And that's what we see. The yellow vector there, it represents gravity. And as we progress, and as I let it run again, okay. If you notice, then the length of that acceleration vector does not change. At the very top there, if you notice, then the acceleration vector is still downward, and it's still going to be negative 9.8. It does not change the whole way through the path, the projectile motion path there. It does not change until it touches the ground again. When it comes to the stop, no more acceleration. The acceleration vector is gone. Okay. All right. Now, so that's what I want to make sure you understand, that when we work through these problems, then that the only acceleration is going to be along the vertical, and that acceleration is going to be negative 9.8 meters per second squared, because the only force acting on this object is going to be gravitational force. Okay. All right. Next thing I want to point out to you, and just as a quick review here, and let's take a look at the velocity vector. Okay. So when we fire this object out, okay, the velocity vector, as you notice, let me go ahead and put that up. Okay, first of all, if you notice, the velocity vector is not straight up, and the velocity vector is not straight to the side. It is up and to the side. It's up, it has a vertical and a horizontal component to it. So this is what we refer to then right here. This is what is referred to then as the initial velocity. As soon as it leaves, and it's and again, remember, there's no other forces acting. As soon as it leaves, this is what we refer to as the initial velocity. That is v initial right there. Okay? And if you notice then, after it leaves, and let me go ahead and let's get it going here. Okay. Whoops, sorry. Okay. Okay, there it is. As you notice now, the vector is changed. That velocity vector is going to change. So this is no longer the initial velocity. The initial velocity is right when it leaves the cannonball. Okay, right when it leaves and leaves the ground. Okay, all right. So this is velocity at some other time. And if you notice here, this velocity here is also up and towards the right. It's going to be up and towards the right as the cannonball progresses on its pathway. Okay? And so I'm going to let it continue to go. And what I want to point out to you is right there. Oh, sorry. I wanted to catch it right at this point right here, at the very top. So if you notice, at this point right here, at the height of the pathway, and I'm going to go ahead and draw this here. Okay, at the top of the pathway right there, this is the height, the highest it's going to get. Okay, if you notice, if I had stopped right there, this velocity right here is what we refer to as the velocity at the height. Okay, and that the velocity max. Okay, at the very height of the pathway, and if you notice, then it is pointing it's pointing directly towards the right. Again, it's kind of tilted downwards a little bit, only because I didn't stop it in time. But if I had stopped it right there, the velocity at this point then is pointing directly towards the right, directly forward. There's no part of it that's moving up or no part of it's moving down. And so therefore, at this point here, you're going to notice then that the velocity vector is pointing only towards the right. If I can let it continue to go, you're going to notice then that the velocity vector is going to start to change its direction now. Okay, now it's now pointing down. So the whole time, the velocity vector is kind of pointing up, pointing towards the right. Okay, pointing towards the right. Initially, in the first half of the pathway here, in the upward trajectory, it is pointing up and towards the right. In the downward trajectory here, if you notice that it's starting to point down now and towards the right until we get right before. Well, I'm trying to pause it right there. Okay. Right before it hits the ground, then this is what we refer to as V final. That's our V final down here. Okay. This is the velocity right before it touches the ground, because right when it touches the ground, and I'm going to show you this right here, it's when it touches the ground, done. Velocity is gone. Why? Because it's come to a stop. And so V final is not the velocity when it touches the ground, it's the velocity right before it touches the ground, and that's how we define it right there. Okay. All right. So hopefully you had a chance to see that. Now, with that said, then I want to go ahead and share with you the components. Okay, so let's go ahead and let's take a look at that. Let me leave this here. Let's fire the rocket again. All right. Oh, my components aren't there. Sorry. Let me go ahead and clear up that pathway. Okay. All right. So let's take a look at the components here. Oh, what happened to our components? Oh, yeah, I'm sorry. There it is. Sorry. Let me start that again. Okay. All right. So we saw then the velocity vector without the velocity vector, the one arrow that was up and moving towards the right in the upward trajectory, and downward and towards the right in the downward trajectory. Okay. Let's go ahead then and let's take a look at what happens here. So let me go ahead and fire the cannon. Okay. Let me pause it right there. Now remember, and I want to point this out to you, the initial velocity, and this is what we had. The initial velocity was that way. In the initial state, the initial velocity was that way right there. That was our initial velocity right there. Okay. All right. So with that said, then what we have here are the components of the initial velocity. Okay, the components of the initial velocity. Because why? Remember, the initial velocity was up and towards the right. So here is the rightward motion, and we call that the x component. X component of the initial velocity. The initial velocity in the x direction, because it's moved. This vector here is moving towards the right, but it's also moving up at the same time, and so we call this then the initial velocity in the y direction. Okay. So that's what we have right there. Those are what we refer to as the components. Okay, and so how would we obtain the components here? Well, we would need to know then this angle right here, which is our launch angle, which we would call theta. Okay, that angle is going to be measured off the horizontal right here. This is the horizontal surface here, so we can measure that angle as well. And so therefore, to find then, and I'm going to go ahead and write this in, to find then the initial velocity along the x, what would we do? We would take then the cosine of theta. Okay, and if you notice that there, if we drew this in, if I connected the arrows here, let me just go and do that really quickly. If I just shifted this arrow over to here, what you would notice then is that we would form a right triangle. So there's our right triangle. Okay, so all I do is move this v sub y, v naught y, the y component of velocity over here, and then we have our y component. And so therefore then, if we take a look at this, then there's our right triangle with the angle theta right here, and the initial velocity itself, v naught here, as the hypotenuse. And so to solve then for the x component here, we would take the cosine of theta and multiply it by v initial. Okay. To find then the y component of the initial velocity, we would take the sine of theta and multiply it by v naught. Okay. And so that's what we have right there. And this is everything is here's review. What I wanted to do is, as we continue this, and let me go ahead and let this go. What I want you to do is I want you to notice what happens to the x and the y components here as we progress. Okay, so let me go ahead and pause it right there. If you notice that as we pause it, as I let it go, what happens to the y component? The y component is getting shorter and shorter and shorter as it moves up until it gets to the very top right here. And I'm going to try to stop it as soon as I can. There, 0. I did it. All right. At this point, then, if you notice, then the only component, the only velocity component, like I pointed out to you for this cannonball, is the x component. At the very top here, the only velocity that we have at the very top here, the only velocity that this cannonball has is the velocity along the x. So we have then v sub x here at that very top there. Now, as you notice, as it moved up, and hopefully you notice, and folks, you have access to this. So if you need to go back and play around with this a little more to see what I'm pointing out to you, please do so. This will help you understand projectile motion. At the very top there, if you notice then, the x component never changed. And so the velocity here at the very top then will be exactly the same as the x component of velocity that we solved for way down here. Okay, so remember that x component down here, I'll just draw that line in again, that x component down here, we solved for this, we solved for this one by using this equation right here. Okay, using that equation right here. Okay, so with that said, if we can solve then, we can solve for this, we have the velocity at the very top here as well, because it doesn't change. So as I continue to let it go past that point, let's go ahead and see what happens past that point. What do you notice? Okay. The y component of the velocity now starts to increase now. It's going to start to increase, but it's going to start increasing and it's going to point down. If it started pointing up in the upward trajectory, now it's going to be starting to point down. And as you notice, even along the way then, right before you hit the ground, the y, I'm sorry, this is getting, sorry, you can't see that. But anyway, hidden behind that, I'm going to try to stop it right before we get to there. Okay, right there. Right there, the x component has not changed its trajectory. So I let this, so I'm firing off this second cannonball here to get you to see then the x component here and the x component here are the exact same length. The y component here, and you're going to notice this, and the y component here will also be the exact same length, because remember why? And when we have in symmetrical motion, the velocities at the 2 points, the point of when it's shot off, and the point right before it hits the ground, okay, the point where it gets launched up into the air, the point right before it hits the ground, the velocities will be exactly the same. The velocities will be exactly the same. Okay? All right, so that's what we see there. So the components change, okay, and there's, I'm sorry, only one component changes, and that's the y component of velocity. X component velocity stays exactly the same, which corresponds to what we've been saying, that the only force acting on this object is acting in the y direction, along the vertical. There's nothing acting along the x direction, so therefore we expect in that horizontal motion to be that horizontal velocity continue to be the same throughout because there's no acceleration. There's no force acting on the X. There's not going to be any acceleration either. Okay. All right. I know that this is taking a long time. I hope then that you were picking up on all these things while we were doing this. Okay, but one last thing I would just point out to you then, as we go through, then I'm going to be referring to this upward motion here as the upward trajectory, the downward motion is the downward trajectory. The last thing I did want to point out to you then is remember the time that it takes to go up, which we refer to the time it takes to go up is going to be equal to the time it takes to go down. Okay, and so the total time then is going to be time up plus time down plus time down. Now you have to understand this. This total time here also represents the total time it takes to get from the start here all the way to the finish. The time it spends in the air. So if you want to think about this, okay, this is the time it takes. This is the time it spends in the air. Okay, this is the time in the air. Stays in the air. That's exactly the same time here. So this is also T total. That's the same amount of time it takes to get from start to finish. Okay, that has to be the same. And the way we say it then is that the total time along the Y direction, the vertical, is equal to the total time along the X direction. And that is the only the only thing that the motion on the X and motion on the Y have in common in this. Everything else is going to be different. Everything else will be different. Okay? All right, will do. Let me go ahead then, and I want to save this here for you, and I'll post this for you on Classroom. You can have it to study with. And so with that said, then let's go ahead and use this then. And I want to go ahead and I think I have that saved. Let me clear that up. All right, so play around with this FetLab here, you guys. I know that it's not something. This is not Xbox. This is not PlayStation 5 or whatever stuff. But like I said, it is absolutely useful in understanding projectile motion. Okay. All right, so with that said, let me go ahead then and let me share that one. Let me go ahead and let's take a look at the problem that we left off with on Friday. Okay, and let's work through this one here. Okay, let me go ahead and share this with you. So that over there. Some things around here a little bit. Okay. So we left off with this problem on Friday. We didn't quite finish it. Again, like I said, I'm sorry, we had some technical issues on Friday, but let's go ahead and Monday. I'm sorry, Monday. And so let's go ahead and let's take a look at this problem here. And so we left off with this right here. So let me go ahead and recap for you what we were able to come up with here before we finish. Okay. We traced the motion of the long jumper here. We identified the initial velocity here. Now it's the red arrow. And we said we were told that the initial velocity is at 11 meters per second, okay, and at 20 degrees. Now you can use the FetLab to kind of get this done. The only problem then is that when you adjust the little cannon right there, you can't. If you get it at 0 meters, the cannon looks like it falls a little bit below the ground, and so it's hard to get the 20-degree angle here. And actually, it doesn't quite work out exactly the way we're going to work it out here, but it comes close. We use the FetLab to confirm this, okay, and so. But that's what we have there. And then we were able to solve then for V initial X and V initial Y. So again, if you aren't quite sure how we got those, please make sure you review the first part of the video from the lesson from Monday, or just come by and get that extra help. Okay? All right, so in this problem here, we were asked to find then the total horizontal distance. This, remember, is what we refer to as the range. So this is the range right here. Okay, so this is the range. That's what that's what they're asking us to solve for. So we're asked to solve for the range. Okay, so here we have the range. And so the term range there, it means in horizontal distance, delta x. Okay, and then we're also asked to find then the height of the long jumper as well. Okay, and so with that said, then I pointed out to you then we can't at this point. We can't solve for the range. Why? Because we're missing the total horizontal time. Now remember, and this is why I wanted to review with you use the FetLab. that total time is exactly the same amount of time that the object spends, the long jumper spends in the air. So what I was trying to get through to you on Monday was that if we can find the total time that the long jumper stays in the air, we can just plug it straight in there, and we can solve then for the range. Okay? But with that said, then we go back to the horizontal, to the vertical distance here. So we're going to leave the horizontal. We're going to leave the range. We're not going to do anything with that. We're going to ignore the horizontal motion for right now. We're going to go back and we're going to take a look at the vertical motion here. Okay. And so if we try, we can go ahead and we can find this distance here, the height that the object travels at. Okay. And once we have that, we can use the other kinematic equations at our disposal to find the total flight time. And I'm going to do that for you in just a moment. But let's go ahead and let's take care of B first. That is, let's solve then for the total distance in the horizontal, the vertical distance. Now understand, I'm going to show you one way. There's actually another way that you can solve for it. Actually, remember when it comes to kinematics, there could be more than one way to solve for it. But let's go ahead and use this one here, and let's take a look at how we solve for this one. Okay? All right, so with that said, just using this equation here, okay, I rearranged the equations that we can solve for delta y. In order to solve for delta y, we need to get the final velocity along the y, we need the initial velocity along the y, and we need the acceleration along the y, okay, which we have. Let's see what we do have when we work through this. Okay, so we know what the acceleration is. Acceleration is g. I'm sorry, let me go into that. Okay, so we know then that the acceleration is g. So we know the acceleration along the y. That's going to be equal to g, which we know then is negative 9.8 meters per second squared. Okay, so we have that. Okay, do we have the initial velocity along the y? Sure, we do. We just solved for it right here. So we also have the initial velocity along the y, which is the velocity at vertical velocity at this point. We solved for that, and I think we had it at what was it? Where was it? 3.76. Okay, I'm sorry, there it is. 3.76 meters per second in the vertical right there. Okay. Now the question is, what is the final velocity? Do we know what that final velocity is? Now it would be very tempting to say then, well, didn't we say then that this is the final velocity over here, the final velocity right before it touches the ground? I'm sorry, final, not the initial. Didn't we say that that's the final velocity right there, right before it touches the ground? Okay. And if that is the case, then wouldn't then, and since this is symmetrical, wouldn't then the final velocity along the y just be the opposite direction? And let's go ahead and draw that in. Would it be just the opposite direction right there of the initial velocity? And so therefore, we would say then that the final velocity along the y right here should be negative 3.76. Okay? And voila, there it is. We have everything we need. We plug it in, and then you plug it in, and you end up getting 0. You do. Yeah, I think you could probably just do it in your head right here. There it is, negative 3.76. You take the square of that, and then you take minus the positive. You take the square of the positive value of 3.76. That difference up there is going to give you 0. If you can't do that, folks, if you don't see that quickly in your head, just plug the numbers in. You're going to get 0, which is exactly right. That is, we expect it to be 0 because here, if we were saying that this is where it ends up at, okay, then, and this is that starting point, okay, it ends up right where it started out at, and so therefore the displacement will be 0. That makes perfect sense. The problem is where we chose to say the V final, because here, remember, we want this height right here. So the way that we want to imagine this is if we can shoot off, if the long jumper can jump and then stop right there, we can pause him right there at this point. If we can pause him at this point, we can take a tape measure, we can just pull it up, and then we can measure where he's at along the vertical. Okay? Now that is not possible, okay? But we can calculate for it. Why is that? Because we know what the velocity is here at the max. We know what V max is right here. Okay, V max along the x, we already know it has to be exactly the same, 10.3 meters per second. V max along the y, we know that as being 0 meters per second. Doesn't mean that he stops, folks. It does not mean that he stops. It means then that he stops moving up, okay, but he's still moving horizontal. Why do I put that at you? Because let's, again, if we can imagine freezing the long jump at this very top here, okay, and say that that's his final position. If we set that as his final position, we can determine then that distance right there, delta y. And isn't that what we were asked to solve, what we were being asked to solve for here? Absolutely. And so V final in any of these kinematic equations does not always necessarily mean the final position right before the object hits the ground. Okay? V final is any velocity at a position that we want. Okay, so we want to figure out the position here. Okay, and at that position, the long jumper has a velocity, an x and a y. He has an acceleration. He has also a force, and then he also has a distance. If we wanted to find how high up the long jumper was at this point right here, if we wanted to find the delta y at that point, then what we could do, same thing, we can use the initial velocity here, and then try to find, and we can calculate for it, the velocity at this point along the x and the y. But since we're trying to find this vertical distance here, we only need to know the velocity along the y direction at that point, and we can plug that in for v final y. So v final y here, v final here, just simply indicates a final velocity at some point that we want to stop examining, stop the motion. Okay, so at any point along this motion here, we can identify a velocity, and we can use that velocity as the v final. And so therefore, the v final that we will use here is the final velocity along the y here, okay, at the maximum height, at the very top of the motion there, which is going to be 0 meters per second. That is something you really got to make sure you try to wrap your mind around, folks, because that's going to be important here. V final doesn't always necessarily mean the final position here. V initial, on the other hand, okay, for the most part, will always indicate the initial velocity here. Now, with that said, if we wanted to compare 2 points along the pathway here, let's say we wanted to compare a point along here, okay, and here, then we would say that, and we want to find the range there, for example. Okay, how far did it travel from this point to this point here? Then we can use v final, v initial at this point here, and v final at that point. Okay, so we can set v final and v initial wherever we want to, and where we choose to set it is going to help us with solving these problems. So it's up to us. Okay, all right, very good. So there it is. We have everything we need now to solve then for the display, the vertical distance, the height. Okay, so let's go ahead and let's plug it in and solve for that height. Let me go and do that really quickly. A little low on time here again. Okay, so these problems, folks, we are going slow, but I'm going slow intentionally. Hopefully, you get some point then that you won't need to do all this. You're kind of doing all this in your head. Okay, so with that said, then I'm going to plug in the final. That's going to be squared minus v initial, which is going to be positive 3.76 meters per second squared, and that's going to be all over 2 times a negative 9.8 meters per second squared. And if you plug that in, you're going to find then delta y, the height then is going to be 0.721 meters. And that is the vertical distance. There's a vertical distance right there. Okay. All right. Now, that's part B. We got to go back to part A, but before we get back to part A, what we need to do is we need to find the total time of flight. Okay, flight time right there. We now can do, we can go ahead and do this here, and we can use one of the kinematic equations, and I'm going to go ahead and list this here. I'm going to use this kinematic equation here to solve for the time, okay, and hopefully you remember this. We have then v final is equal to v initial plus a times t. This a in the acceleration in the y direction. Okay, so we can go ahead. Let's use that equation right there to solve then for the total flight time. And so the total flight time here, and let's go ahead and indicate this, is going to be the total time that it spends up in the air. The total time that it spends up in the air. This time, if you can see this here, if we use the velocity here again, okay, and let's just continue to use the velocity at the very top here. Okay, so basically here, I'm sorry, let me go ahead and go back to this here. If we find the time that it takes to go up the upward trajectory, so t up right here, Remember, we can T down is exactly the same time. We can add those two together, and then we get the total flight time. Okay, so let's go ahead then and let's solve for that. Okay. All right, so total flight time, we're going to start out with T up, which is going to be then V final minus V initial all over A Y. Okay. In this case then, let's go ahead and identify this here. We know then V initial along the Y is going to be 3.76 meters per second. Okay. V final, again, if we're going to pick this point at the very top here as being our final position, okay, so V final along the Y then is going to be 0 meters per second. And the acceleration along the Y, you guys, it's going to be the same. It's going to be negative 9.8 meters per second squared. So we have everything we need to solve for the upward, the time it takes to go up. So let's go and plug this in. It's going to be then 0 meters per second minus 3.76 meters per second divided by negative 9.8 meters per second squared. And the time that it takes to go up then, let me see, where did I put it? Yikes. I'm sorry, let me go. I think I have it at 3.2. Let me just check to make sure I got that right. Sorry. I don't want to give you the wrong number here. So it's going to be 3.76 divided by 9.8. Yeah, 3.8. A little bit off. 3.8. So I'm sorry, 0.38. So this is 0.38 seconds. That's the time it takes to go up. So that's the amount of time that it takes to move in the upward direction there. Okay, so let me go ahead and do this. So let me take a little bit more time, you guys. This is the amount of time it takes to go up. Okay, we want the total time. Okay, so T up and T down will be the same. So the total time, I hope you recognize it, is we just double the time it takes to go up. Okay, and so the total time then is 0.76 seconds. Okay, all right. Now this is not our answer, and again, I'm sorry I've run out of time, but for the lesson, I'm going to post the lesson. So the Monday, what we'll see on Monday then is we can now take this, because remember the total time it spends in the air is the exact same amount of time that it takes to move from start to finish here. And I think then at that point you should be able to recognize then how we solve for this one. Okay, so we will pick up with this discussion on Monday, you guys, and then please work through these problems here. I'm gonna set I'll change one more time. I'll change the homework. I'll change it till Monday. That'll give you some time to ask me questions on Monday as well. Okay. All right, folks. For those of you folks, seniors who are going to the prayer tomorrow, hopefully you'll enjoy your time back on campus. And for the rest of you, have a good weekend. And then I will see you folks on Monday morning. I'll see you folks on Monday morning. Hold on a second. Sorry, I forgot. Let me save this here. I'll see you folks on Monday morning, and take roll, and then we'll continue with this lesson on the video lesson. Okay. All right. Have a good weekend, guys, and I will. I'll see you on Monday. Okay. Bye.